Cats and kittens, welcome back for your third section for the engineering physics option. Fluids and fluid dynamics. Okay, so one of the things that we're going to talk about quite a bit for this section is a couple properties of fluids that's very important in terms of buoyancy and flow and stuff like that we'll get into. Density and pressure. So just going over, you know what this is already, but just to refresh our memories, density defined as mass per unit volume, and the symbol that we use in IB here for density is this Greek letter rho, R-H-O, and it kind of looks like a fancy looking P there, whereas pressure, force per unit area, lowercase p. Okay, so under a solid object, like say for example, a book sitting on a table, the pressure on the table only acts downward, obviously, since gravity is pulling down. However, the pressure in fluids is caused by the random motion of particles, and it acts equally in all directions. The hydrostatic pressure, so we've got, let's say, water, for example, at a given depth in a static liquid, in other words, it's not flowing, is a result of the weight of the liquid acting on an area, so area A right here, plus any pressure acting on the surface of the liquid. Here we've got a formula. I thought about maybe deriving this for you in this video, and I would normally do that in class, but this video is going to be long enough as it is, and there's also a derivation, a really good derivation of it in the textbook as well. So we're going to leave it there. Pascal's principle. So all liquids are incompressible. In other words, volume cannot be reduced. So you can reduce the volume of a gas, obviously the pressure goes up, but you can't do that for a liquid. And the motion of the particles in the liquid are random. Pascal's principle says the pressure exerted anywhere in an enclosed static liquid will be transferred equally to all parts of the liquid. So word problems are going to involve things like hydraulics, for example, where it's a very simple ratio. This is what it looks like in terms of the formulas that you're going to have to do. Pressure is force per unit area. So notice the pressure exerted anywhere in an enclosed liquid. So here we've got pressure at location 1, pressure at location 2 is transferred equally to all other parts of the liquid. Archimedes' principle. Buoyancy is the ability of a liquid to provide an upward force, sometimes called the upthrust, on an object placed in or on the fluid. So dealing with things that are floating. Okay, so here we've got a cylinder of fluid inside a liquid. Because of the increased depth, the pressure on the lower surface, so it's lower down than liquid obviously, will be slightly greater than the pressure on the upper surface, literally because there's more liquid above the lower center than the upper center. And you've all experienced that when you sort of dive down into the deep end of a pool or something like that, you can feel the pressure on your ears. So the buoyancy force, B, is equivalent to the weight of the fluid displaced by the cylinder. So here you've got the density of the fluid, mass per unit volume, the volume of the fluid, and G, obviously, acceleration due to gravity. Again, for the purpose of this video, I'm throwing up a formula there, identifying the variables. For extra context and the derivation of it, please read the textbook. Okay, so here we've got floating. The boat floats because the weight of the fluid displaced right here, that's that shaded area, must be equal to the weight of the boat. If more weight is added to the boat, it's going to sink lower into the fluid, so lower into the water, to displace a weight of fluid equal to its new weight. If this is not possible, so it can't displace that much fluid, then at that point the boat will sink. fluid dynamics. So now we're going to start talking about fluid, not static, but moving, so flowing down a pipe, for example. So a fluid is in hydrostatic equilibrium if it's either at rest or any parts of it that are moving have a constant velocity. So it's kind of like static equilibrium in terms of like, I don't know, any object where the forces acting on it are balanced. Okay, so this occurs when forces are balanced by differences in pressure. In the case of a floating boat, its weight is balanced by the pressure differences in the water. So you get that buoyant force. An ideal fluid, so sort of like an ideal gas, but obviously for a fluid, has constant density and is incompressible, has constant pressure acting equally in all directions, is non-viscous. So viscosity is something like, let's say, maple syrup or something that would be a very viscous liquid. It's thick, it doesn't flow very quickly, whereas something that is less viscous, like water, for example, flows very quickly. And has a steady flow pattern that can be represented with streamlines. We'll talk about that right now. Okay, so streamlines right here. Streamlines are lines that show the paths that objects would follow if they were placed in the fluid. So here you've got streamlines just of a fluid flowing down a pipe here, for example. So the properties of fluids cannot be fully explained only by the behavior of individual particles they contain, like an ideal gas. So we idealize the flow of a fluid as what we call laminar flow. The movement of layers sliding over each other, just kind of like playing cards, without any movement of fluid between those layers. So here we've got a representation of laminar flow. And you've seen probably pictures of, let's say, a wind tunnel where you've got like some smoke in the wind tunnel or whatever, and here you've got air flowing around a tennis ball. And we notice the paths of the smoke here around the ball form these streamlines. And when the streamlines are uniformly distributed, you've got this what we call laminar flow. Whereas if you've got turbulence, you call that turbulent or non-laminar flow. Okay, so let's deal with this now quantitatively. The continuity equation. So we've got a picture right here like this. We've got, again, laminar flow down a tube, except where we've got our cross-sectional area in different parts of the tube different. Here we've got a large cross-sectional area. Here you've got a smaller cross-sectional area. So it's kind of like taking a tube where water is flowing through it, or a hose or something, and you squish part of it. So the mass per second entering and leaving a tube must be constant. So we call that steady flow. And because the fluid is incompressible, the flow speed then therefore must increase when the tube's cross-sectional area decreases. So you've experienced that before probably, where you've got a garden hose and you want to spray the water on the end. All you got to do is sort of put your thumb over the end, and you're decreasing the cross-sectional area, and what happens is the fluid speeds up on the way out. So the constant is referred to, this constant right here, is referred to as the volume flow rate and is measured in units of cubic meters per second. The Bernoulli equation. When an ideal fluid flows through a system at a steady rate, the total energy of the fluid, so we've got potential and kinetic, and the work done remains constant. So here's your kinetic energy, here's your potential energy, and work done, pressure times volume, that equals a constant. So what we've got here is dividing by all these terms by volume right here. So 1/2 mass divided by volume gives you density. Here we've got mg but mass divided by volume again gives you density, and you divide pressure times volume divided by volume, and you've got pressure. The Bernoulli effect. So, if an ideal fluid is flowing horizontally, or an object is moving horizontally through a fluid without turbulence, there must be a decrease in pressure wherever the speed increases. So this has to do with airplane wings and curved balls and stuff like that. So the Bernoulli effect can be used to explain a curveball pitch in baseball. So let's say a baseball player puts a spin on a baseball as it's flying through the air. So here we've got a baseball flying to the left here across our screen, and we have a clockwise or counterclockwise rotation like this. The motion of the ball's surface will increase the speed of airflow on one side, bottom in the diagram, and it's going to decrease it on the other side, at the top of the diagram. So it's moving this way, so it's increased the speed on the bottom and decreasing on the top. So this causes a pressure difference, and that means then the ball is then forced down in this case. Same thing with an aircraft wing called its aerofoil. So here we've got the same thing. So here's a shape of an aircraft wing like this, and because you've got it's sort of fatter on the top and flatter on the bottom, the streamlines are closer together on the top here, further apart on the bottom. So higher speed, there we have for a reduced pressure, and lower speed on the bottom. That means you've got increased pressure, so that produces our lift. We've got increased pressure on the bottom, decreased pressure on top, upward pressure on the bottom. That causes lift. Venturi tube would be an example of that, using that same Bernoulli effect. A fluid flowing through a tube will have less pressure where the tube is narrower, because the fluid must flow faster. So here we've got a wider cross-sectional area. Here we've got a smaller cross-sectional area. The fluid here is moving at a higher speed because the streamlines are closer together. And notice we've got lower pressure here because the water that's pushed up into the tube here, Venturi tube, is moving at well, not moving, but the water here is moving at a higher speed, so it exerts lower pressure. So notice the water level here is a little bit lower, versus on the either end here, we've got a lower speed because of the bigger cross-sectional area, and the fluid then exerts a higher pressure. So pitot tubes. This is an example or an application of a Venturi tube using that same property, where the speed can be used to, well, the difference in pressure exerted by air allows the airspeed of an airplane to be measured. So it's like a speedometer, it's essentially for airplanes. So, like it says here, speed of an object moving through a fluid. The principle of a pitot tube relies on comparing the pressure in the direct flow of the fluid, right here, versus somewhere else that is not in direct flow, so right here. And again, going through this relatively quickly, we've got support here with another link, a video down in your Google Classroom assignment that you can take a look at. Also, it's mentioned in the textbook as well. Flow out of a container. Here's another, just a quick example from your textbook as well. You've got essentially let's say a graduated cylinder with sort of 3 holes drilled into it, and you've got water streaming out. So at each of the holes, the pressure is equal to the atmospheric pressure right here. However, the lower you go inside the fluid, as we learned before, the greater the pressure exerted by the fluid. So that kind of makes sense. The greater the pressure difference between the inside and the outside, the further the water is going to go. So using that same equation that we learned about before. Okay, viscosity. We mentioned viscosity is a measure of a fluid's resistance to flow. So something like, again, corn syrup or something like that would be a high viscosity, whereas like rubbing alcohol would have a low viscosity. So ideal fluids, just like ideal gases, are just a model. And since real fluids have some frictional forces between different layers and the outer layer in any container. So just like a real gas, there is intermolecular forces between the molecules. But viscosity can be considered as a measure of a fluid's resistance to flow, like I just mentioned. So when an object moves through a fluid, it will experience what we call a viscous drag force. So Stokes' law allows us to calculate the size of this force only with spherical objects with smooth surfaces moving through a fluid within laminar flow, or with streamline or laminar flow. So what you do essentially, and I've seen a few students do IAs on this in the past, where you imagine, like, say, like one of those big graduated cylinders with a certain amount of fluid in it, and you can take like a marble or a ball bearing or something like that, and if you've got, let's say, a graduated cylinder with water and a graduated cylinder with syrup or something like that, when you drop a ball bearing through those fluids, obviously the ball is going to get through the water faster, and then it's going to go move slower through the more viscous fluid, the syrup or something like that. So based on this experiment, by measuring the speed of a ball as it falls through a fluid, essentially, you can get what is called the drag force, and then you can find out the coefficient of viscosity. So calculating the viscosity. Turbulent flow. So before we talked about laminar flow, where all those streamlines are even and parallel to each other. However, we've also got some turbulent flow right here. So to quantify that, we have what is called a Reynolds number. So Reynolds number, capital R, gives us an idea of how fluid will flow through a pipe. As the mean speed, V, of a fluid through a pipe of radius R increases, the laminar flow becomes less likely and turbulence may begin. So as a rule of thumb, if the Reynolds number is less than 1,000, we can expect laminar flow. So here we've got the speed of the fluid, the radius of the pipe, the density of the fluid, and the coefficient of viscosity. What was called the coefficient of viscosity? Yeah. Okay, so that's a quick journey through fluids and fluids dynamics. I didn't want to make those videos too long because anything around, I don't know, 15, 20 minutes starts to get a little bit, you start to kind of drift in and out kind of a thing. So I wanted to keep them relatively short and have you guys work on the practice problems. So I want you guys to read pages 570 to 581 and then practice the questions in the handout. All right, that's it for today. See you guys.